Okay, so here's where we were last time. Well, this is where we left off, I guess. This is the next thing we were going to do. So we're going to look at this surface with that equation near a certain point. Wait a minute, we've done this example kind of before. Let's go back a page. Look at this. Same surface, same equation near the same point we've already looked at. And what we've already done, just to be clear, is we've addressed the question, is x locally a function of y and z? The way we did that is, keep in mind whatever variable you want to view as a function. You take the partial with respect to that variable. What do you take the partial of? You take the partial of the function whose level set you're looking at, right? And so following those rules from the implicit function theorem, we take the partial, plug in the point in question, and we get not 0 as the value, and not 0 means yes, we're all good, yes, you can view x locally as a function. Okay, so that's what we've done already on this example. So notice I've got that indicated here. We've already established that x is locally, near that point, locally is a function of y and z. Okay, we are now going to ask sort of a follow-up question, which is, what is the partial of x with respect to z? Noticing, as we should, that the thing that we are taking a partial of here, x, right? Not anywhere in the equation is it indicated as being a function. So again, we're hesitant to take a partial of something that we were not told is a function, but we've already established that it is by our own efforts. Right. So it's okay to talk about a partial of x because it is locally a function. How do you compute its partial? Well, we're just going to use this formula from the previous page, and it's largely plug and chug. You compute the appropriate partials of f. You divide. You don't forget the critical minus sign, and done. All right, how are we doing? Is everybody on board? Okay, so that's the part we didn't finish last time from this section. Pretty short. I do want to remind you of a couple of things, though, just to make sure. Again, I've already said this, but I'm going to say it again. This minus sign right here, so important, extremely important. Not only does it make the formula true as opposed to false, right? But without that minus sign, if you don't have that minus sign, look at what this formula becomes. This formula becomes seemingly a suggestion that you can kind of cancel the partial f's, and that feels like your partial xi kind of just, again, denominator of your denominator and all that business. And it looks like it ought to just kind of work, except that this is absolutely invalid reasoning. This is fundamentally misunderstanding what's going on with implicit differentiation, right? So the minus sign here is the only thing that distinguishes a correct answer from what at a glance really appears to be just fundamentally misunderstanding the entire subject. So, gosh, that's such an important minus sign because of, again, that role that it plays in how your work looks. So please don't miss that minus sign. It's just so important. Okay, next thing, and I wrote about this in the email I sent on Wednesday. On a question like this, what I have highlighted in green here, not the question that was asked in this example. But if you have a question that says, hey, here's an equation, and near a certain point, what's this partial? Notice, in what is circled in green, again, there is no suggestion in what is written in green that x actually is a function, and that you can even talk about what these partials are. Right? So when you see an example, an exam question, homework question, what have you, such as what's in green, notice that you really do have to do two things. You have to first do what we did over here. You have to first establish that it actually is, that x actually is a function of y and z. This would probably be about half of the points on such an exam question, for example. Got to do that first. And once you have established that x indeed is locally a function, then secondly, and only then, can you reasonably write down this formula and compute as we've done here. Right, so 2 parts to the question. Again, point-wise, this is probably about half the points on the question, and this is probably about half the points on the question. Does everybody follow the suggestion I'm making there? Okay, cool. Alrighty, so moving along. This finishes chapter 2. We're going to move on now to chapter 3. Actually, we're going to skip over, of course, 3.1 because we already did it. We did 3.1 because I needed that point of view in order to be able to talk about a certain point of view of the chain rule that we've already covered that ground. Okay, so on with 3.2. So, how do I compute the length of a parametric curve? Let's see, I hit the wrong. Okay, so what we call arc length. So given a parametric curve, how long is that total parametric curve? Okay. So I'm going to set up some tools, some machinery to help us do this. And in fact, the tools that we're going to set up here are going to be useful in other circumstances as well. We're going to use this setup a lot, for example, when we get to chapters 6 and 7. It's going to be a really big deal. But we have some uses for these things now, so let's go ahead and set it up now. Okay, so looking at a parametric curve, maybe we have some big, long parametric curve like that. We're going to look first at just a little piece of it, a little differential piece of that parametric curve. I want to, first on that little piece, talk about this vector. And I'm going to call it dx. And this is my differential approximation of my displacement along this little piece of curve. So I was here. dt seconds later, I'm actually here. But while I was at this point, I wasn't able to, all I know when I'm at this point is the velocity. I didn't know the curve was going to, curve. So while I was at this point, the best estimate I could make was that my differential of position would be about like this, and I was close, right? But anyway, not quite exactly. So this dx vector is the very first thing that I want to talk about. It is, like I say, literally the differential of your position function x. And so you're going to hear me casually referring to this as the position differential. Again, because it's literally what it is. It's the position differential, dx. And I hope it comes as no surprise that it's x prime dt. You can think of this a couple of different ways. You can think we would write x prime as dx dt and then solve for dx. If you want to think of it that way, that's fine. You can also think of this as a kind of a basic fact of geometry or physics, that displacement is velocity times time. Also, a perfectly reasonable point of view. And, of course, x prime being the same at, x prime being the same as velocity, you can also think of dx as being v dt, same thing. Okay, is everybody good? All right. Now, what about this ds thing? The actual length of this piece of curve. Now, I remind you, there's a difference between a displacement, which is a vector, right, and a distance, which is a scalar. So this ds thing here, we're actually trying to talk about the length along that piece of curve. Our linear approximation of the length along that piece of curve would be, well, it'd be the length, be the magnitude of this dx vector. So, there you go. Yeah. Everybody okay? All right, yeah. So ds is the magnitude of the dx vector. Is that cool? Everybody happy with that? Okay. And being the magnitude of the dx vector, and the dx vector, of course, being v dt, no surprise that the magnitude of that is magnitude of v times dt. Okay. All right. now what's the deal then with this thing? Let's see. Oh, color choices. I'm going to use blue. This vector right here. This is what we call the unit tangent vector. You can see it. Someone's going to participate in this discussion over here in just a minute. But what can we say about this unit tangent vector? Well, it points in the direction the curve is going, because it's tangent vector. Well, so does the velocity. Velocity also points in the direction that the curve is going. So if t is going to be a unit vector pointing in that direction, then you just take the velocity vector and make it a unit vector by dividing by its own magnitude. Is that cool? Okay, so what are we going to do with that here? I'm going to make the argument that this is another point of view on what the dx vector is. I claim dx can be thought of as t times ds. And there's two different ways that you can see this. First, let me make the intuitive hand-wavy pitch. These two vectors, dx and tds, I claim they have to be the same because they both point in the same direction. Right? What direction does dx point? Well, it points in the direction the curve is going. What direction does t point? It points in the direction the curve is going. These two vectors point in the same direction. And what's their magnitudes? Well, dx, its magnitude is ds. What about this product right here? What's its magnitude? Well, don't forget t is a unit vector, so the magnitude here also ds. Right? So these two vectors point in the same direction, have the same magnitude, they are the same as vectors. You buy it? Everybody happy? Okay. All right, an algebraic point of view. Don't forget that we have a formula for t right there. And don't forget we have a formula for ds right there. And so if I were to multiply green times blue, I get that times that. And notice magnitude of v in the denominator cancels with magnitude of v in the numerator. You get v dt, which is dx. So, different way to think about it, if you prefer. All right, so with all of that set up, we are now ready to actually compute the length of a parametric curve. Here's our parametric curve, like that. I've got a formula right here for how to compute the length of a little piece of it. ds is v dt. Right? That computes the length of that little piece. If I want to compute the total length, I'm just going to add up over the entire curve. And lo and behold, there you go. That's how we compute length. It's this integral that I've got down here. Yes?
So when we say curve, like parametric curve, does it mean parametrized curve?
Yep. Yeah, parametric curve means a curve attached to the parameterization, namely the formula that gives you position as a function of time, typically. Yeah, totally. Yep. All right. Okay, so let's see an example. The bad news, by the way, about these examples, if you look at this integral, you look at the integrand of the integral. The integrand you see here has, well, it's a magnitude. Magnitudes, of course, are square roots. Square root of the sum of the squares of the coordinates. That's how you compute magnitudes. And right off the bat, we're scared of the integral because integrals of square roots, we have a lot of experience with these being hard to do. So in this case, notice again, because we're computing the magnitude of the velocity, we take the derivatives of the position to get the velocity and compute the magnitude, and there's your ugly integral that is going to actually be pretty darn hard to do. And I don't want to do it, and I don't want to make you all do it. So sadly, this does tend to work out this way, that these integrals just tend to be bummers. And so there's two possible ways that this can work then on an exam. One thing I might do is I might go to whatever trouble is necessary to arrange for certain nice things to happen to where amazingly, unexpectedly, this thing under the radical is a perfect square. And if you can make that happen, if you can make this a perfect square, then the square root is actually something you can just write down, and then you can compute it. And there are some cases where that can happen. I'll show you an example on the next page. The other possibility would be that it's not nice. And the question would then be, set up but do not evaluate an integral that would compute the length, blah, blah, blah. Right? So that does, I've got a long history of doing questions of that form on exams as well. But fear not, I won't have an exam question where the integral you need to compute is undoable. That wouldn't be fair. Okay. All right, so let's talk about a reparameterization. I'm going to start by observing that this curve here, this parabola, can be parametrized different ways. This parameterization, for example, you can plug in the formula for x, the formula for y, right into that equation. The equation works. So that is one parameterization of that curve. But here's the thing. So is this. You take that formula for x, you take that formula for y, plug into this equation, the equation still works. Now, hopefully no surprise, right? There's lots of parameterizations of a curve. Intuitively, why is that? Don't forget, one way to think of a parameterization is it is a process of drawing your curve. Well, there's lots of ways to draw the curve. You could draw it at sort of a unit speed, or you could draw it really fast at the beginning and then kind of slow down and then speed up at the end. Or you could go really slow at the beginning and then move really fast and then really slow at the end. These all draw the exact same curve. Right? So no surprise that there are lots of parameterizations of a given curve. In this case, we can actually relate these two parameterizations. Notice that if I just let t equal to q cubed plus q, and plug that into the left parameterization, that immediately gives me the right parameterization. So, nice little moral here. Whenever you can find an algebraic relationship between parameters, you can turn one parameterization into a new parameterization by just literally plugging in for what your first parameter is, and then everything will come out in terms of the second parameter. So this is called a reparameterization. Now there's a specific reparameterization that I want to talk about. It's called the arc length parameterization. And it is a tricky, clever idea. The idea is that if I have some existing parameterization, let's suppose I think of position in terms of t. So at that point right there, for example, let's suppose I think of this as being where I am at time at where t equals some given fixed value t. Right? All I have to do to reparameterize is find an algebraic relationship between t and something else. And here's what that something else is going to be. That something else is going to be arc length. Specifically, the amount of length that I have drawn out between wherever I started when t was 0 and wherever I am at this given value of t. So, for any given t, there is a corresponding s. And we have the formula for what s is on the previous page. It's this integral right here. Now there is a weird thing about what I've written down here. I know it's weird. Let me address it. Notice that t is playing a role here, that it is the upper bound. It's the upper bound for this integral. Right? I want to know how much arc length is created between when time equals 0 and a given future value of t. So t is a bound. And you can't confuse your variables. You can't have t also be a dummy variable. It's not allowed, right? So t already being the thing that is the upper bound, I have to use a different letter here. This is the lowercase Greek letter tau. Looks kind of like a t. I still want to think of this as playing a role kind of like time, so I like the Greek letter tau for this purpose. Tau is going to be the thing that actually moves along from 0 to t. So the integral has to be in terms of the dummy variable tau, can't be in terms of t. I hope that is okay. Is satisfactory. You might recall there's a similar move that gets pulled when you're looking at one of the, let's see, I guess they call it the second version of the fundamental theorem of calculus. They have to do a kind of a similar little kind of rewrite in order to have everything actually make sense. Okay, so having done this, and you've got s as a function of t, just turn it around, solve for t as a function of s. Take that formula for t as a function of s, put it in there, and out comes, you'll notice, position as a function of s. Position as a function of s. It's called the arc length parameterization because we're literally using arc length s as the parameter. All right, now let's talk about how to visualize this. I have a favorite metaphor for this. Think of this as being a road. Right? We've talked about roads as being parameterized before. Think of the parameterization, this initial parameterization that we had, x of t. Think of that as describing the road trip. As I personally drive along the road. And as I personally drive along the road, I am at a certain position at any given point in time t. Okay? So, with this metaphor of, I'm driving along the road, what is s? And the answer is actually a very simple thing. S just represents the mile markers on the side of the road. I don't know if y'all are aware, if y'all noticed, but if you're driving along an interstate, I believe, for example, there are going to be mile markers about once every mile. 168, 169, 170, etc. Right? And that tells you how many miles you are away from some fixed base point. And I have to admit, I don't know if that's like, I think it might be like the state capitol or the courthouse or, something along those lines. Probably varies from road to road. So that's exactly what S is. And if you think then about, what would it mean to parameterize the road on the basis of mile markers? Well, that just says, all right, when S is 0, I'm at the courthouse. When S is 1, I'm a mile down the road. S is 2, I am 2 miles down the road. And that is giving you position as a function of how far have you driven. It was ultimately pretty natural. Think about it. Everybody okay with that? Okay. All right. So why do we like arc length parameterizations? And there's a couple reasons. I like to point out that it is intrinsic to the curve. It's natural. Let me highlight this better. Intrinsic to the curve. It's natural because it doesn't depend on anything arbitrary, such as how fast you're driving. Right? If I don't know, decide I'm going to break the record and drive from here to Wilmington as fast as I can, right? Well, that'll give me a different parameterization of the road than if I'm driving nice and slow and reasonably. Which one's the right parameterization? Which one's natural? Neither. They're arbitrary, right? But the mile marker parameterization is always there. It's always the same. It doesn't matter who's driving. It doesn't matter how fast you go. Doesn't matter when you make your drive. It's just always there and natural. So it's an intrinsic and natural thing, and that's fundamentally good. It has unit speed, I claim. This is a nice observation to make. If you view position as being a function of s, which is itself a function of t, write down the chain rule as it applies to this sort of sequence of functions. The chain rule looks like that as a result. And now take a magnitude of both sides, and let's ask the question then, what is this thing? That's the magnitude of the velocity vector, aka the speed. And what is this thing? Well, that's distance per unit time, aka speed. So these things are equal to each other, and it therefore immediately follows that this thing here is 1. So, nice little handy dandy little proof. Okay. Alrighty, so it's unit speed, it's intrinsic to the curve, it's a really good thing. And by the way, I'll point out that partly because of these reasons, it is extremely useful to have arc length parameterizations or to assume or discuss arc length parameterizations when you're trying to prove theorems in geometry. Now, that said, how do you find an arc length parameterization? Well, it's usually not very easy. As you're about to see, this is I'm going to call it a carefully constructed example where I've gone to some trouble to make the integral doable. And even still, this is going to be kind of a failure of an attempt to reparameterize. So here's my position. Taking the magnitude, don't forget magnitude is the square root of the sum of the squares. You got to take the derivative to get the velocity, and you multiply this all out. And let's see here. Notice we have a perfect square there. And then notice what this does. This thing turns the green perfect square into this orange perfect square. It turns this minus 2 tau squared into plus 2 tau squared, effectively then turning this minus into that plus. Wasn't that clever? I wish I'd thought of that on my own. I didn't. Somebody showed me this many years ago. So every so often you'll get lucky. Again, now notice that this is the example I was promising on the previous page. When the stars align, you find yourself with a square root of a perfect square, which goes away. You then get a reasonable integral, and bam, cool, there's my relationship between S and T. Seems like a happy ending, except, remember, in order to do the arc length parameterization, I need to solve for T as a function of S, and I don't know how to solve cubics. Right? So, even though this was carefully crafted, it's still kind of unworkable. Yes?
So can you talk about how you got from the sum to the perfect square?
The what now?
How did you go from the sum of the thingy?
From here to here?
Well, the second line from the left to right.
Oh, okay. Yeah. So, if you so here we have 4 tau squared, and I'm going to add that to this minus 2 tau squared, and that adds up to plus 2 tau squared. And with a plus in this position instead of a minus, there's a minus sign in some sense because of that minus sign, and having turned it into a plus, that would be what I get if I have a plus right there. It's just an algebra thing. Does that make sense? Yeah. Cool. Okay. All right. On to the next section then. By the way, there are some homework exercises where you will do arc length reparameterizations, and there are some examples where it actually goes through just fine. And the thing is, again, it's really hard to find examples where the whole thing goes through just fine. You can see I got kind of stuck at this point. Anyway, the examples that are in the Kali book are set up to where everything that you need to do goes through just fine. It's ultimately not hard. You're going to be, you got to be careful with the algebra, but anyway, carefully crafted and all that. Okay, so new object of study. Now we're going to talk about something called a vector field. Vector field is a a very important mathematical construction because there are a lot of natural, real-world, physical objects of interest which, if you want to describe them, if you want to write them down mathematically and get some business done, yeah, they're vector fields. So this construction that we're about to define is the perfect tool for describing lots of reality. So anyway, let's define it, and then I'll talk about what it's good for. Vector field is a function. It's a function from Rn to Rn. Notice this n and that n have to be the same. Let's see here. Now the specifics of how we view this. The input you should view as being a point in space. You know, whatever your Rn is, either R2 or R3 or whatever. So view the input as a point, but then view your output not as a point. View your output as a vector with its tail at the given input point. All right, so when we say vector field, we mean a function of this description, but specifically we mean that we're going to view it in this way, where we think of the input as a point, we think of the output as being what we call a field vector that, in some sense, I think of as happening at that point. So we get pictures that look like this, and I guess I'll go ahead and observe that this is, the fifth different kind of picture that we're drawing in this class. We have, let's count. Graphs, level sets. There's what I like to call the literal picture of a function. When we draw parametric curves, we're drawing the image of the function. These are all that we've already got 4 different ways of viewing functions geometrically. This is now number 5. Right? And you've got to make sure to remember what calculus looks like in all of these different pictures. Totally different. Okay, so y'all have heard me say that enough. I'll leave it at that. Okay, so what does this look like? What is this? I mean, physically, what concept gets conjured here? For me, I don't know, I look at this and I see a fluid flowing across a surface. Right? Maybe this is the surface of a river, and I feel like the arrows are representing how the river is flowing wherever you might happen to be. Here I see, I don't know, maybe like an airflow. Maybe there's an updraft of air. I don't know, like next to a cliff. Have y'all seen those videos on like Reddit or whatever where the birds don't flap their wings? They just kind of hold their wings out and they just go right on up the cliff. Right? Pretty cool. So something like this. This is I see here a suggestion of a flow of air going generally upward and maybe off to the side over here. So fluid flows. Now this is a very natural physical phenomenon. Fluid flows. And this new mathematical construction called a vector field is the perfect mathematical tool to represent those fluid flows. Okay. Alrighty. So, see some examples just to kind of get a few wins under our belts. Here is a vector field, and let's look at the input point, x comma y. Some point there. And then what's my field vector? The output, 2 comma 1. Well, that'd be about like this, I suppose. So there's one point vector pair representing what the field looks like at that point. But now what about other points? What about here, or here? Well, notice conveniently it's the same field vector. It's 2 comma 1 everywhere. So we get this same arrow, same vector everywhere on that across the XY plane. So there's a rough picture of what that vector field looks like. What do you think? Everybody on board? We call this, I hope it's not surprising, we call this a constant vector field because the field vector is a constant. It's always the same. Specifically what I mean by constant here, I don't mean that this is not changing with respect to time. There is no time in this story. But constant in the sense that it's independent of x and y. Okay. Right, here's the next one. Let's look at this vector field for a given input point x comma y, such as this point right here. Now let me take a pause before I go on. That's a point, but don't forget points come as equivalent, connected to, however you want to say it, their corresponding position vector. And if you look at what this is saying, what this formula up here is saying, it's saying that the field vector and the position vector are the same. So when I draw this green arrow, what I'm going to be drawing is, I'm going to be deliberately drawing a vector that is the same vector as the position vector for that input point. What do you think? Everybody see how that works? Okay. So if you repeat this for a bunch of different points, notice that wherever you might happen to be, whatever point you're at, the field vector is always going to point away from the origin, radially away from the origin, and with magnitude equal to the distance from the origin. And so altogether then that gives you this picture right here. Everybody see that? Okay. It's kind of weird. Algebraically, you look at this and you're like, oh wow, this is the nothing happens vector field. It looks like you might even want to call this the identity vector field. And yet the picture is pretty non-boring, right? I mean, there's seemingly something happening here. So, again, vector field pictures are a completely different way of understanding a function geometrically, and so how we interpret these pictures is something we're going to have to develop. Yeah.
When we're drawing vector fields, how many vectors do you want us to draw?
Yeah, that's a great question. I'm going to say always just draw enough to be representative, enough so that it's clear what the pattern is, right? So if I were to, this is a dumb example, if I were to say 1, 2, 3, 4, dot, 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 you know what I mean. But if I say 1, dot, 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 I don't know what that means, right? Right? So just make sure that you draw enough for the pattern to be clear. So I've drawn arguably more than I really needed here, right? I think that's, if I'm counting right, that's 24. And that's, you don't need to draw 24 most of the time. Yeah. Cool. All right. Okay, here's another one. So again, thinking about this input point, arbitrarily I'm going to pick, let's say, that point right there. Keep in mind, points are associated to their position vectors. There's the position vector. Don't forget, I can draw that position vector anywhere I want. Now, just for convenience, I'm also going to draw that position vector right there. Same vector. Vectors don't have a location. I can draw them wherever I want. The reason I want to draw it right there is that notice there is a relationship between the position vector of the point and the field vector that I need to represent at that point. And specifically, now this is a callback to linear algebra. Remember, one of the big prerequisites that I'm going to need you to know from linear algebra is how to understand certain geometric transformations like rotations as being linear transformations that can be represented by matrices, that can be understood by their columns, which are the images of the standard basis vectors, etc. Right? And so, not hard to show. I'm going to let y'all do the linear algebra on this, but not hard to show that what turns the position vector into the field vector, it's a quarter turn counterclockwise, and so that turns into this. So let me get rid of all the junk then, at this purple point, we get this green field vector. Likewise, do that for a bunch of different points, and all together you get this picture. Everybody okay? All right. Let me remind you about that linear algebra business. If you're a little shaky about it, come talk to me in office hours. I'll be happy to walk you through it. I want to make sure everybody's good to go with that. It is important. It is going to be really useful in this class. Come talk to me, and we'll make sure that you're good on that part of linear algebra. Yeah? Oh, yeah, sure. I mean, sure. Let me pick just to get some numbers down here. Let's look at f of, I'm going to say 2, 1. And what does that equal to? Well, let's see. First of all, 2, 1 is a point that's about right there, let's say. And let's see, according to this formula, 2, 1, the field vector would be -1, 2. And this field vector, -1, 2, is about like that. And notice, as I had claimed, the position vector and the field vector are rotations of each other. Yeah, and you can plug in as many points as you like here. Pick any point you want, write the x and y coordinates, follow the rule to get the field vector, and you're always going to find that you get one of these. You get part of this. I like to think of this as a stirred pot, right? And it'll always follow that pattern. Yeah.
-1, 2 is this. How do we know?
How do I know what now?
-1, 2 is an error of that direction.
Yeah. So keep in mind, this is the color mistake. The first coordinate is the horizontal component. That's why I went kind of back to the left there, right? And then the second coordinate is the vertical, and that's why I go kind of up. Is that cool? Yeah. All right. Okay. So here's a really important vector field. This is called an inverse square radial vector field. It does not appear to deserve that name. When you look at this formula here, doesn't it look like it should be inverse cube? Right? But the slick move here is to rewrite this like this. What's nice about this point of view is what's on the right here now I can view as being a unit vector. So this part in orange serves only to give a direction to this vector field. That's a unit vector. And so the magnitude is what's left over, and this is clearly an inverse square magnitude. The unit vector, of course, you'll notice is the unit vector pointing in the direction from the origin to the point. In other words, it is radial outward from the origin, thus the term radial inverse square. Now, how come these arrows that I've drawn here are pointing toward the origin instead of away from the origin? Well, C is negative in this picture. Why did I choose a negative value of C? Well, because that's what gravitational fields look like. Right? The nature of gravity, and I think this is ultimately a good thing, is that it is inward. It is, two pieces of mass attract toward each other, not repel away from each other. So gravitational forces intrinsically attracting, and so you get inward arrows. Electric fields have the same form, but electric fields, of course, depending on the charge of the particle, could be either inward or outward, and so, whatever. Okay. All right. So we're going to do a lot of things with this vector field when we get to chapter 7 in particular. Here's another example. Oh, by the way, I'm just realizing I forgot to plug in my power. Let me plug this in before I run out. There we go. Gradients. Now, we've already talked about gradients. Gradients always point uphill. When we were talking about gradients, I didn't say anything about vector fields. I claim that gradients are vector fields. And the reason I didn't say anything about it is because at the time we didn't know what vector fields were, and it wouldn't have made any sense. But so let's just notice, if you have a real valued function such as this one, and you take the gradient, here you go. Notice it's a vector field. Given any point x, y, this is a formula for a field vector. 2x, 2y. Right? And this is something that looks kind of like this. It's, points outward away from the origin, not unlike this one, right? Points outward away from the origin. And just to track some old news, we already knew that gradients are supposed to point uphill on the graph. And notice, if we look at a graph of the function whose gradient we took, and if we look at the gradient in the domain of that same function, indeed, these gradient arrows, all of them, the entire vector field, always pointing uphill, wherever you might happen to be on that graph. So, just an observation that we, without even realizing it, had already seen a bunch of vector fields in the form of gradients. Everybody okay with that? A little bit of foreshadowing. Just want to let you know. You can look out for this more when we get into chapters 6 and 7. But not only are gradients vector fields, they are special and important vector fields. And exactly how special and how important, we're going to have to wait until chapters 6 and 7 to see. Okay. All right, a little bit of terminology. Hopefully no surprise when you're talking about applying the gradient operator. If you give me some function, what comes out when you take the gradient is called the gradient of that function, whatever it is that you took the gradient of. So again, I don't even know how to say that. It's a tautological. The gradient is the gradient. Right? Okay. However, what would you call the other way? What if someone gave you a vector field and said, I want you to find the function whose gradient is that given vector field? In other words, I want you to go backwards through this arrow. I'm going to give you the vector field. I want you to find the function. Because you're going backwards through that arrow, I propose that it'd be reasonable to call this the anti-gradient of the vector field that we were given. I mean, this is I'm piggybacking off of the terminology derivative and antiderivative, right? Same structure, same concept, just applied to gradient instead of derivative. Okay, this is my preferred terminology, but I have to admit that I'm I'm outvoted on this. The far more common term for this thing, for this anti-gradient, is to call it the potential function, which doesn't seem to immediately explain itself. Right? Why would we call it the potential function? The reason why is because there's a particular reality of physics in certain situations that you can have potential energies, and you take the gradient, and the gradient of potential energy is force. So it's just very commonly the case when you're doing physics that you're interested in forces and you're also interested in potential energy. If you've ever had a mechanics class, you know that these are the heavy players in doing mechanics. And so what I would call the anti-gradient, well, in a physics context, it's potential energy. So potential function kind of makes sense. And let me make this there we go. Okay, so you're probably going to hear potential function quite a bit more. Now let me tell you why I don't like this term. There's two reasons. One of them is, sometimes, believe it or not, when we're doing math and talking about gradients, sometimes we're not actually interested in physics at all. Sometimes there's no force involved at all, and I'm not talking about potential energy at all. Why should I use terminology that assumes a physical scenario that's not even happening? I think it's weird. I don't like it. To me, anti-gradient always makes sense. It says exactly what it is. I think it's just more reasonable myself. But here's the worst problem with this. You may have noticed this minus sign right here. If you think about it, let's talk about gravity. Potential energy, when you're talking about gravitational potential energy, is higher when you're higher up, and it's lower when you're lower down. If you write down the function, it's a constant times z. You take the gradient up. What direction is the gravitational force? It's down. So minus sign, right? So not only are we sometimes not talking about physics and don't want to think about potential energy, in fact, the anti-gradient is not even technically potential energy. It's the negative of potential energy. Drives me crazy. So anyway, so these are your terminology options, and why those are your options. You're going to hear me say anti-gradient in this course because I think it makes more sense. Outside of this course, you're probably going to hear potential function more than the other. Okay, and I guess that's where we're going to have to draw the line for today and this week. See y'all on Monday. I hope you all have a good weekend. Don't forget to check off on attendance before you go if you can.